In the last lecture, we were looking at some elementary problems on multivariate analysis and some problems on multivariate normal distribution. Let us continue with these problems until we solve all these problems. So, we are discussing this problem number 6 here, where we were given for the 4-variate distribution the mean vector given by this mu vector and the covariance matrix given by this sigma matrix. We had let us see, we had completed the problem number A of this, that is, we had looked at what is the covariance of AX1 derived from that multivariate vector, and covariance of BX2, and also further what we had done was to find out what is the covariance between the two components AX1 and BX2. Let us now move on to this problem number B of problem number 6, part B of this problem. So, here we are trying to find out what is the joint distribution of AX1 and BX2 if we have the joint distribution X following a multivariate normal 4-dimension. Let us see how to obtain that. So, for this B part here, the given conditions are that we have X a 4-variate normal with a mean vector mu and a covariance matrix sigma, where this mean vector mu was as given earlier. So, that is 4 3 2 1. So, this is 4 3 2 1. We had this sigma matrix, the 4 by 4 symmetric positive definite matrix, which was given by this particular quantity here 3022. Then the other elements were 1 1 0, then it was 9 minus 2 and 4, 9 minus 2 and 4. So, this is a symmetric matrix, so no need to write the lower diagonal part here. Now, what in this problem we are trying to find out the joint distribution of AX1 subvector and BX2 the second subvector. Now, note that these subvectors were defined to be the following quantities, that X1 was given by this and X2 was given by this, right. And accordingly, what we had seen is that the covariance matrix of X1 subvector was given by this 3229 matrix, and the covariance matrix of X2 subvector derived from this covariance matrix of X was given by this 1004. So, this is what we have. Now, in order to find the joint distribution, what we will define is this, whose joint distribution is required to be obtained, BX2. Now, here let me make it complete, that this X1 subvector was, let us see, that was X1 X3. So, this was X1 X3 the two components, and this X2 subvector is this X2 and X4. And what we had also obtained in the last lecture was covariance matrix of X1 to be 3229 and the covariance matrix of this X2 subvector was derived as 1004. Right. Now, if we look at this z vector here, which is having this as the first component and this as the second component, then if we look at alpha prime z, now this is going to be linear combination of the elements of the original x vector. The original x vector is 4-dimensional, x1, x2, x3, and x4 transpose. So it's a 4 by 1 vector which is having now a multivariate normal distribution. So if we look at this particular alpha prime z, now this is going to be linear combination of the elements of x only, right. So this is nothing but linear combination of elements of x. Now x has got a multivariate normal distribution. So by the definition of multivariate normality, that x will have a multivariate normal distribution if and only if every linear combination is going to be a n1 random variate, and hence this alpha prime z, which is nothing but linear combination of elements of x, is going to be distributed as n1. So this is going to be distributed as n1. This is true for every alpha in the appropriate space generated by this dimension of this particular vector. What's the dimension? We may note that this A was given by, let's see, A is 1 by 2 and this B is 2 by 2. A was 1, 2, so this is 1 by 2. This B was a 2 by 2 matrix, and hence the order of this particular subvector is going to be 2 by 2. And what about this one? Now this is going to be A multiplied by that 2-dimensional vector. So this is 1 by 1, so it's a scalar random variate. So this Z has got the order that it is 3-dimensional, and hence this alpha, that's what we are taking for checking whether it's a multivariate normal distribution, is this alpha belonging to r to the power 3. So for every alpha belonging to r to the power 3, this alpha prime z, nothing but a linear combination of the elements of the x vector, the original 4-dimensional vector, is going to be n1. So this would imply that this z vector, which is 3-dimension, is going to be a multivariate normal 3-dimension with expectation of z and the covariance matrix of z, right. So let us now find out what is this expectation z and this covariance matrix of z that will actually complete this particular problem. So expectation of this z vector is nothing but expectation of this particular element out here. So that would be given by A times expectation of x1, and this is B. A and B are non-stochastic matrices. So this is going to be given by this particular element. Now expectation of x1 and expectation of x2 are simple to be obtained. We had expectation of x vector to be given by this. So if x1 is x1 x3, then expectation of x1 would be 4 2, that particular subvector. So here what we have is the following, where expectation of this x1 subvector is the corresponding elements from there. So that's 4 2, and expectation of x2 subvector similarly, that's going to be given by 3 1, because the elements are 2 4. So that this is 3 1. So this is what is the expectation vector of the z random vector. So let us denote that by mu z. So this is by plugging in the value of the A vector, B matrix, expectation of x1 as given here and expectation of x2 as given here, one can obtain what is the explicit form of mu z. Now the last thing that we need to compute is covariance matrix of this z vector. So what is that? So if we look at this covariance matrix of z, covariance matrix of z is the covariance matrix of this blocks Ax1 and Bx2. So this would be given by, I think we had obtained this term earlier. So this, the covariance between the two Ax1 and Bx2 is going to be A sigma, or rather the covariance between x1 and x2, which was given by this, and this is the B transpose matrix, that's what we had. So using those, what we can write here is that the first block would be the covariance of Ax1. So that is going to be A times covariance of this x1 subvector times A transpose. This is going to be B, the covariance matrix of x2 subvector multiplied by B transpose, and then this part is the covariance between Ax1 and Bx2, so that this is A times covariance of x1 subvector with this x2 subvector, that multiplied by B transpose, and this is just the transpose of this particular entry sigma 1 2 out there. Now we have already computed the constituent elements of this A covariance matrix of x1 into A transpose was given here. So this is covariance of Ax1, which is A, covariance matrix of x1 A transpose, which is given by this, and we had also obtained covariance matrix of Bx2, which was this particular element here, which was this particular element, and furthermore we had this covariance between Ax1 component and Bx2 component given by this, and hence we already have all these elements already computed, are already computed, so that we can denote this particular term by this sigma z matrix, so that we have the joint distribution. This would imply that the joint distribution of A x1 and Bx2 is multivariate normal given by this z vector, which is Ax1 subvector, Bx2 subvector, that follows a multivariate normal 3 dimension with mu z as its mean vector and sigma z as its covariance matrix, which is the desired joint distribution as what was required in this particular problem out here, right. Now the C part of this problem is that with the same assumption as what we had made for the B part of the problem, that is a 4-dimensional multivariate normal with the given mean vector and the covariance matrix sigma, find the marginal distributions of x1 and x2, and the conditional distribution of x1 given x2 is this particular quantity. So this is the C part of this problem. Now we have x following a multivariate normal 4 dimension with mean vector as mu and covariance matrix as sigma. Now x1 is a subvector derived from this x here, and hence this is going to be a 2-dimensional normal distribution or a bivariate normal distribution with mean as mu1 subvector and a covariance matrix as sigma 1. Now we have already obtained these elements, so this mu1 is equal to expectation of this x1 x3 subvector, which we have already computed, and sigma 1 is the covariance matrix of x1, which also we have computed. So this is basically the marginal distribution of x1. Similarly, x2 the subvector, which is comprising of the second and the fourth element in this x vector, that's also a bivariate normal distribution with mean vector as say mu2 and covariance matrix as sigma 2, where this mu2 is expectation of the second subvector x2 and sigma 2 is the covariance matrix of the second subvector. Sigma 2 is the covariance matrix of x2 subvector, which once again both these elements we have already computed. So these two are the two marginal distributions of the two subvectors x1 and x2. The last part is to look at the conditional distribution. This conditional distribution of x1 given x2 subvector as 2 1 So this is what we are trying to find out. Now in the theory lectures we have seen that if we have such a partition, then this x1 given x2 equal to small x2, the given specified vector, which is 2 1 for this case, is also a multivariate normal with the dimension of this x1 subvector, which is being conditioned by the other subvector. So this mu2 would be given by this multivariate normal 2 dimension will have a mean vector as mu1 plus sigma 1 2 sigma 2 2 inverse x2 minus mu2. So this is going to be the mean vector corresponding to this multivariate normal, bivariate normal here, and the covariance matrix, say it is given by sigma 1 1 dot 2, where this sigma 1 1 dot 2 is given by sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 2 1. Now these partitions are nothing but actually the following, where sigma 1 1 is the covariance matrix of x1 subvector, that is the notation. Sigma 2 2 is the covariance matrix of the second subvector, which is x2, and sigma 1 2 is the covariance matrix of x1 and x2, and sigma 2 1 is just the transpose of that sigma 1 2 matrix, right. So if we have these the elements, then what we are having was actually this joint distribution of x1 x2 rearranged vectors, actually rearranged elements forming into the new vector, and the conditional distribution x1 given x2 equal to small x2, which is this one, would be given by this particular multivariate normal distribution with this as its mean vector and this as its covariance matrix. Now note that we have already computed mu1, we know what is sigma 1 2, that is the covariance between x1 and x2 subvector. Sigma 2 2 inverse is the covariance matrix of x2, we have also obtained that. x2 small x2 is this particular vector 2 1 here, mu2 is the subvector. It's better to use a similar notation, so that this mu1, if that is the subvector corresponding to the first element, this is the mean subvector corresponding to the x2 subvector. So we know all these quantities, and sigma 1 1 dot 2 can be computed from here, because sigma 1 1 is known to us, sigma 1 2 is known to us, sigma 2 2 inverse, and sigma 2 1 is known to us. So that completes this particular problem of finding out the conditional distribution of x1 given x2 equal to this 2 1. Let us now move on to the next problem. We have x, a 2-dimensional normal with a mean vector mu and a covariance matrix sigma, where mu is given by 2 2 and sigma is an identity matrix of order 2. A is this vector of 1 1 and B is a vector 1 minus 1. Now the problem is to verify whether Ax and Bx are independent or not. Let us see how to solve this particular problem. We have this x vector, a 2-dimensional normal with a mean vector mu and a covariance matrix I2, where this mean vector is having its entries as 2 2, and A is 1 1 and B is 1 minus 1. So we have A as 1 1 and B as 1 minus 1. Now the two quantities in which we are interested in is Ax and Bx. Now what can we say about Ax and Bx? Now Ax is going to be a normally distributed random variable. It is going to be a univariate normal, because this is a 1 by 2 vector, row vector, and hence this is going to be distributed as an univariate normal distribution, and so will be the distribution of Bx. But that is not exactly as important in order to verify whether the two random variables derived from the random vector x are independent or not. the thing that would be of interest is to look at what is the distribution of Z. Now let us define this Z as AX and BX. Now what is going to be the distribution of this particular Z vector? Now we can write this as A B times this X vector. So this is some C matrix. Now what is the order of this C matrix? A is 1 by 2, B is 1 by 2, and hence this is a 2 by 2 matrix. So this is a 2 by 2 matrix, C times X, right. Now X has got a multivariate normal distribution. In the theory lectures what we had proved is that Cx also has a multivariate normal distribution, so no need to look at it fresh and then take linear combinations and argue that every linear combination of that has got univariate normal distribution, and hence the joint distribution would be multivariate normal. So this is going to have a multivariate normal distribution with mean vector as expectation of Cx and the covariance matrix as the covariance matrix of this Cx, which we can obtain very easily. What is that? So this is going to be an N2 with C times mu as its mean vector. C is that matrix and mu is this vector of 2 2, and this is going to be C sigma. Sigma is this I2 matrix, so C I2 C prime, right. So this Z vector, which is having Ax and Bx as the two constituent elements, so this is a two dimensional random vector which is having these two, the two quantities in which we are interested in, that has got a multivariate normal distribution. So since it has got a multivariate normal distribution, in order to see whether they are independently distributed or not, well, one can actually look at the joint distribution, or rather the distribution of Z, and then try to find out if the joint distribution of Ax and Bx is in the form of the product of the two respective marginal distributions, but that is a cumbersome way of checking. Well, this is simple in this particular problem, but a better way would be to look at, since we have got the joint distribution to be multivariate normal, if we just compute what is the covariance of these two elements. If the covariance is 0, then the two random variables are going to be independent, because we have the joint distribution to be a multivariate normal distribution. So the thing of interest would be to look at what is the covariance of Ax and Bx. So the covariance of Ax and Bx would be given by A covariance matrix of X, that is I2, and then B transpose, right. So this is the covariance between Ax and Bx. Now let us see what is this equal to. So this covariance of Ax and Bx is given by A sigma. Now that sigma is what we already have as I2. So A I2 B transpose. Now A was given by what? 1 1, and B was given by this 1 minus 1, 1 1, then this is I2, and this is 1 minus 1. So this is 1 1 1 minus 1. So it's 1 minus 1, and that is equal to 0. So since we have the covariance between Ax and Bx equal to 0, and the joint distribution of Ax and Bx to be a multivariate normal distribution, that would imply that Ax and Bx are independently distributed. That completes this particular problem. So this is done. Let us look at the next problem. We have these xi's I equal to 1 to n are independently distributed multivariate normal distribution with mean vector as mu and the covariance matrix as sigma. We are trying to find out the distribution of this particular quantity where these ai's are real constants. So let me try to look at how to solve this problem. This is problem number 8. Problem number 8 is what we have as xi's following np with a mean vector mu and a covariance matrix as sigma. I equal to 1 to up to n are independent NP distributions. Now the quantity of interest is AI xi I equal to 1 to n, right. So we are trying to find out the distribution of this particular quantity summation AI xi. Now let us denote this by a vector y, which is just the linear combination of these. This actually is the result corresponding to the univariate result, where we know that linear combination of any univariate normal distribution is also having a univariate normal distribution. So this basically is that actually. This is the linear combination of n independent multivariate normal distribution. So that's also going to be having a multivariate normal distribution. Now how do we prove that this is going to be a multivariate normal distribution, and what are going to be its parameters? So this y is having the same dimension as the dimension of x. So this is a p by 1 vector. So for every alpha belonging to r to the power p, this alpha prime y is nothing but alpha prime of this summation ai xi I equal to 1 to n. So this is equal to summation I equal to 1 to n ai alpha prime xi, right. Now each xi is having an univariate normal distribution. So this alpha, for every alpha belonging to r to the power p, as what we have taken, this alpha prime xi is going to be an univariate normal distribution. So this is going to follow an n1 for every I equal to 1 to n, and for every alpha belonging to r to the power p. So each of these distributions for every alpha and for every I in this summation are going to have a distribution which is a univariate normal, and hence the linear combination of those univariate normal distribution is going to be an univariate normal distribution. So this follows n1. So what does that imply? For every alpha belonging to r to the power p, this alpha prime y has got an n1 distribution. So this would imply that this vector itself, from the definition of multivariate normality, that this y vector will follow a multivariate normal distribution np with expectation of this y as its mean vector and the covariance matrix of y as its covariance matrix. So in order to complete this problem, what we would require is to find out what is expectation of y and what is covariance of this y vector. So expectation of this y vector is nothing but expectation of this summation ai xi. Now each of these ai's are multivariate normal, p dimension, with a mean vector as mu vector, so that this is nothing but we can take expectation term by term. So we will have this as expectation of each of these xi vectors, and each of them, remember, has got identical distribution, which is that mu vector. So this is, each one of them are going to be mu vectors. So what is this? This is going to be given by, this mu is thus constant irrespective of the ith component, and then this is summation ai. This I is from 1 to n. So this completes the first part of it. This is this component expectation of y computed. So let us look at what is covariance matrix of y similarly. So covariance matrix of y, from its definition, is expectation of y minus expectation of y vector into y minus expectation of y transpose, right. So this is equal to expectation of summation ai xi I equal to 1 to n, this minus this particular quantity, which we can write as summation ai times this mu vector I equal to 1 to n, and then the transpose of this particular entry out here. So that this is of the form that it is summation ai I equal to 1 to n xi minus this mean vector mu, that multiplied by its transpose. So it's ai xi minus mu whole transpose. Now if we take expectation of the products that would come from this particular expression, they are going to be the following. So let us just look at this in a simple way. So this is a1 x1 minus mu, so that's the first term in this n term summation out here, and this is the last term an xn minus this mean, and then we will have the n terms corresponding to this entry out here. So there are n entries out here, so we will have this as a1 x1 minus mu its transpose plus the last term, which would be an xn minus this mu transpose, right. So we are going to take expectation term by term for the entries of this particular product. Now let's see what's going to happen if we take expectation term by term. If we look at the first entry here, now remember that xi's are independently distributed. So the first term here, when it is multiplied with all these n terms here, what happens to the first term is the following, that it is a1 square into expectation of x1 minus mu into x1 minus mu its transpose. Now the second entry here, this element multiplied by all the rest of these n minus 1 entries here will lead us to 0, because xi's are independently distributed, and hence the covariance between x1 and xi for I not equal to 1 would all be equal to 0. So there will not be any contribution when this element is multiplied with the rest of these n minus 1 entries on the second quantity. Now the same thing is going to happen if we look at any entry from here, and then we will have only the corresponding similar entries from the two giving us non-zero contribution. So what we will be having when we take expectation term by term in this particular product is that the first element, when multiplied by all these elements and then expectation being taken, only the first entry is non-zero, which is given by this, and all the rest of the n minus 1 entries will be all zeros. And the same thing is going to happen when we look at each of these n entries here. The one corresponding, the same element corresponding to this, when expectation being taken over it, is non-zero, and similar entries will come up. And so the entry corresponding to the nth term, where this one multiplied by all these n terms, only the product expectation of this particular product is going to remain, which is going to be given by an square, and then the covariance matrix of xn, which is nothing but the sigma matrix which we started. So this is xn minus mu into xn minus mu its transpose. All the rest of the entries will be zeros. So this, each of these entries now are sigma matrices, because we have x1 x2 xn IID as normal multivariate mu sigma. So each of these entries are sigma, and thus this is nothing but summation ai square I equal to 1 to n times, this is a scalar constant that multiplied by this sigma matrix. So that's going to be given, that's going to be the covariance matrix of this y vector, which completes the problem, where we have obtained that this linear combination of these multivariate normal n IID is having a multivariate normal with expectation of y given by this, and the covariance matrix being given by this. So let us move on to the next problem, which is problem number 9 in this problem set. So this is this, where we have x, a multivariate normal distribution, 3 dimension, with this as its covariance matrix, where rho is actually lying between, strictly lying between -12 and 1. Note that this particular range of rho would be required in order to ensure that this sigma matrix is positive definite, right. And we are trying to find out what is the joint distribution of this x1 plus x2, first element, x1 minus x2, the second element. Now this is very straightforward from what we have already solved the problems. So this is problem number 9. We have x, the 3-dimensional vector, to have a multivariate normal distribution with the mean vector as mu, and a covariance matrix as sigma, where sigma is given by, let's see, that's 1 row, 1 1 1, and rho on the all the off diagonals So this is with the restriction that minus half less than rho is less than 1. This would ensure that this is positive definite. And what we are trying to find out is the following: the joint distribution of x1 plus x2 and x1 minus x2. So let us define this vector y to be x1 plus x2, and this is x1 minus x2. Now it's straightforward to see that this can be expressed in this particular form. So if we keep this x1 x2 here, then by pre-multiplying that with the matrix 1 1 and 1 minus 1, so this is what is the quantity of whose joint distribution we are interested in finding out. So this is what, this is a subvector, say x1, where x1 is having the two quantities x1 and x2 as the two entries. Now what is the distribution of x1? What can we say from the distribution of this x, which is 3-dimensional? Now x1 is the subvector which is having the first two entries in this particular random vector, and this is a subvector of a multivariate normal distribution, so that itself would be having a multivariate normal distribution, a bivariate normal distribution here, with the mean vector as the corresponding expectations, expectation x1 as its first entry, and then expectation of x2 as its second entry. This is expectation of x2, and then the covariance matrix of x1 x2, the x1 subvector, would be derived from here, so that this is 1 rho rho 1. So that's simple. Let us denote this by mu1 subvector and this by sigma 1 matrix. So let us have this particular notation going with n2, so that we will have this x1 random vector to have this distribution, and then we are interested in finding out the distribution of y, and that's trivial. So this would imply that this y, which is a x1, will have, now what is the dimension of A? A is a 2 by 2 matrix, so this is a 2 by 2 matrix, and hence this vector bivariate 2-dimensional vector would be having a bivariate normal distribution with mean as A mu1 and the covariance matrix as A sigma 1 A transpose, and that's the solution, because A is given by this, mu1 is this particular part here, and this sigma 1 is given by 1 1 rho rho, right. So this is the desired joint distribution of this x1 plus x2 as its first entry, x1 minus x2 as the second entry of this particular random vector. So this completes the proof of, or rather solution of 9. Let us now look at the solution of problem number 10 and 11, which should complete the problems of this particular set. What is problem number 10? We have x, a multivariate normal 2-dimension, with this as its covariance matrix. We are trying to find out what is the distribution of this particular quantity. Let me carry forward this information. What sigma as its covariance matrix, and where sigma is 3 2 2 2, sigma is 3 2 2 2. So this is a positive definite matrix, and we are trying to find out mu is any vector that may be specified. Y is x1 square, y is, so we are trying to find out distribution of y equal to x1 square plus 3 by 2 x2 square plus minus 2 x1 x2. So this is minus 2 x1 x2. So we are trying to find out what is the distribution of this particular random variable. Now note that this is actually a quadratic form in the components of this random vector x. So we actually would write it in the way the quadratic form results in theory were actually presented. Note that this particular quadratic form can be written compactly in the following form, that this is x1 x2, which is x vector, nothing but x vector, and then the following matrix, which is having the square entries corresponding to x1 is 1, corresponding to x2 is 3 by 2, and then the off diagonals are going to be x1 x2 terms. Now that is going to be half of each of these terms, so that x1 x2 product had a coefficient -2, so that is divided equally into the two off diagonals, and then this is x1 x2. So this is nothing but of the form that it is x transpose A matrix. A is a 2 by 2 matrix, that multiplied by x. So this is a quadratic form, the type of quadratic form results for which we have actually done in the theory lectures. So we are trying to find out the distribution of this. Now remember what the type of result that we had actually proved in theory is that, I'll just put it in a bracket to recall the following result, that if x follows a multivariate normal with a mean vector mu and a covariance matrix sigma, and if we have a real symmetric matrix, then x transpose Ax, I'll say that will follow a chi prime square with rank of A as its degrees of freedom and non-centrality parameter as mu prime A mu, if and only if A sigma is idempotent. So this result can be used in order to solve this particular problem. That's what we had, this random variable expressed in the terms of this quadratic form. That is, using this result, our y random variable, which is expressed in the form that it is A transpose Ax, will follow chi prime square with rank of A as its degrees of freedom and mu prime A mu as its non-centrality parameter, if and only if the A that we have defined, this is our A and this is our sigma, if and only if this A sigma is idempotent. Now it is easy to see actually that this A, where this A is what we had obtained here as 1 3 by 2 minus 1 minus 1, 1 3 by 2 minus 1 minus 1, and sigma is the variance covariance matrix, which is 3 2 2 2. It is easy to check that this A sigma, that's what we have, is idempotent. Is idempotent as A sigma into A sigma is equal to A sigma. One can easily verify this by simple matrix multiplication, and hence this would imply that our random variable y, which was that quadratic form, follows chi prime square with rank of A as its degrees of freedom and mu prime A mu as its non-centrality parameter. Now what is rank of A? Where rank of A is rank of this matrix 1 3 by 2 minus 1 minus 1. It is easy to see that this is of full rank and hence this is of rank 2, and whatever be the mean vector specified, then that would actually lead us to the explicit form of this non-centrality parameter. Otherwise we have y, this random variable, a chi prime square on 2 degrees of freedom, and the non-centrality parameter being given by mu prime A mu, where A is given by this matrix and mu is the mean vector, right. So that solves this particular problem. We will look at the next problem, which is problem number 11. This is y following a multivariate normal n dimension with x mu as its mean vector and its covariance matrix as In, where X is n by p matrix of constants and mu is a p by p vector of constants, then we are required to find out the distribution of this quadratic form. Let us see how to get this problem done. So, this is what is our given condition. So, Y is an n dimensional multivariate normal with a mean vector as x mu and I n as its covariance matrix. Now, we are trying to find out the distribution of y prime I n minus x transpose x inverse x transpose times y, right. So, the question is to find out what is the distribution of this. Now, this problem once again is in line of finding the distribution of quadratic forms, because this is a quadratic form. So, we can denote this particular matrix by a matrix A and then verify whether the conditions for this quadratic form to follow a chi-square distribution are satisfied. Now, the variance covariance matrix under this setup is I n. So, this y prime a y, this y prime a y will follow a non-central chi-square on rank of A as its degrees of freedom, and now the mean vector corresponding to y is x mu. So, that we will have this as x mu transpose A x mu, this as its non-centrality parameter if and only if. Now, since sigma, the associated variance covariance matrix is I n, we will require the condition that this will follow a non-central chi-square if and only if A is idempotent, right. So, let us see whether that condition is satisfied for this particular quadratic form and what is the rank of A in under such a situation and what happens to this non-centrality parameter x mu transpose A x mu. So, this matrix A in the present situation is our I n minus x transpose x inverse x transpose. So, what is A into A? That is I n minus x transpose x inverse x transpose into I n minus x transpose x inverse. So, this is basically the projection matrix. So, this multiplication readily will actually lead us to observe that this is nothing but I n minus x transpose x inverse x transpose, which is nothing but A matrix. So, this would imply that A is idempotent in our case. So, this quadratic form which we have here will follow a non-central chi-square as of now. We will compute what is rank of A and what is this non-centrality parameter in order to complete this particular problem. Now, A is idempotent. So, what we have is rank of A is rank of our I n minus x transpose x inverse x transpose. So, this rank is equal to trace, it is an idempotent matrix. So, that we will have this as x transpose x inverse x transpose. So, this is trace of A minus B. So, it is trace of A minus trace of B. So, we will have this as trace of I n minus trace of x transpose x inverse x transpose. So, that this is equal to n minus, now trace of this quantity is trace of x transpose x inverse into x transpose x. So, this is an IP matrix. So, that this is equal to n minus p, where p actually we assume that x is having full column rank. X matrix what we had in this problem was n by p. So, we assume that x is of full column rank, that is rank of x is p, and under that condition x transpose x inverse is a p by p matrix which is non-singular, and hence this is IP and this is n minus p. Now, what happens to the non-centrality parameter? We were supposed to have the non-centrality parameter as the following. Non-centrality parameter was this x mu transpose A is our In minus x, x transpose x inverse, x transpose x times mu. Now take this x transpose from the left hand side and x from the right hand side. So pre-multiplying this particular quantity with x transpose and post multiplying by x, what we will be having is the following, that this is mu transpose and then this is x transpose x minus x transpose x, x transpose x inverse, x transpose x, that multiplied by this mu vector. Now what is this equal to? This is equal to identity matrix of order P, so that this is finally equal to x transpose x minus x transpose x only, that multiplied by mu prime, and hence this is equal to 0. So the non-centrality parameter of this quadratic form y transpose ay is equal to 0, and hence we can finally write the distribution of the quadratic form in which we were interested in. So this y transpose In minus x, x transpose x inverse, x transpose y, this thus follows. Now the non-centrality parameter being 0 implies that the non-central chi-square is actually a central chi-square, so that we will have this as a central chi-square random variate with degrees of freedom as rank of A, and rank of A we had derived as n minus p, and the non-centrality parameter vanishes. So this actually is the desired distribution of the quadratic form in which we were interested in. Now as an application of this particular result, we will see that suppose we have a multiple linear regression problem, multiple linear regression setup, where we have y equal to say x beta plus epsilon, with the assumption that epsilon follows an n-dimensional multivariate normal with a mean vector as a null vector and a covariance matrix sigma square In. This is the standard setup for a multiple linear regression problem. So in such a situation, this would imply from the assumption on epsilon that this y also follows a multivariate normal distribution n dimension with a mean vector as x beta and a covariance matrix as sigma square In, right. Now under such a situation, what we usually look at is the following form, which is the residual sum of squares denoted by RSS at the point beta hat, the least squares estimator. But before that, let me just for completion's sake write what is the least squares estimators. The least squares estimator of beta, the linear regression parameter vector, is given by this beta hat, which is x transpose x inverse x transpose y. Now if we look at the quantity which is y minus x beta hat transpose y minus x beta hat, so this is the residual sum of squares at the least squares point. So we can replace this beta hat by this x transpose x inverse x transpose y. It is easy to see that this form here reduces to this y transpose In minus x, x transpose x inverse x transpose y, x transpose y, right. So if we have this to be the quadratic form, we see that we are of course interested in finding what is the distribution of this particular residual sum of squares, which is given by this. It tallies with the quantity of interest in the problem that we had, this y transpose In. So this result actually can, the previous problem's result can be used to derive the distribution of this. Now with just a bit of caution that we are looking at this y transpose In minus x, x transpose x inverse x transpose y, when y follows x beta multivariate normal n dimension with mean vector as x beta and a covariance matrix as sigma square I n, right. So, if we are looking at the distribution of this with y following this, the only point at which this derivation of the distribution of this differs from the previous problem that we have just now solved is that the previous problem was solved under the assumption that the covariance matrix of y is I n and this has got a sigma square term present in it. So, in order to find the distribution of this, what is usually done is to look at y prime I n minus x transpose x inverse x transpose this divided by sigma square y. Now, considering this particular element as the matrix A, we will be able to show that this A times sigma, which is this sigma square I n, so that we will have this to follow a chi prime square on rank of this A matrix and a non-centrality parameter to be given by this x beta transpose this A matrix times x beta if and only if our A times the sigma matrix under this situation, which is sigma square I n, is idempotent. So, if and only if I n minus x transpose x inverse x transpose by sigma squared, this is our A now, A times sigma, which is sigma square I n, is idempotent. Now, as we see that this sigma square term cancels out, and what we have, the condition for chi-square distribution is that I n minus x transpose x inverse x transpose is idempotent, which we have already proved in the previous problem. So, that this really is idempotent, and hence this is going to follow this particular term, this divided by sigma square is going to follow a chi-square distribution. The non-centrality parameter once again would vanish, and the rank of this A matrix would be rank of this, as in the previous case it is going to be n minus rank of x, which is, if the full column rank is assumed, that is going to be n minus p once again. So, the previous problem result is actually applicable in finding out the distribution of this quadratic form, which is the residual sum of squares with beta being replaced by beta hat, the ordinary least squares estimator, the distribution of that to follow a central chi-square on n minus rank of x degrees of freedom would follow from that particular previous result.